No. That's fine.
Maybe the assessment committee.
Hello. Nice to meet you. You have to keep it together. How are you?
Nice to meet you.
All right.
Nice to meet you.
Hello.
Hello.
You know? Hello. Hello.
Hello, good to see you. It's so nice to first time.
Yeah, maybe for me. Yeah. Should I sit?
Good afternoon, ladies and gentlemen. I'm Associate Professor Troels Pedersen, and on behalf of the section of Wireless Communication Networks and Department of Electronic Systems, I would welcome you to introduce this PhD defense by Ahmed Shawky. Close?
Very close.
The title Quality, Context, Enhancement, and Cost-Effective Radio or Fiber Network Planning. I will first introduce the assessment committee, supervisors, and thereafter I will leave the floor to Steve, student still, who will give a presentation of 50 minutes or so. After that, there will be a short break. If there are any questions from the audience, I would like you to notify me. After the break, we will continue with the examination by the assessment committee. And in case there are questions from the audience, I will reserve some time for that question. We will close no later than 16:15, and there will be some reception afterwards. Frederiksberg is by 7. The lounge. So if you're not local, try to find a local. I'll lead you there, otherwise it's really introduced. So, pleasure to introduce the committee members. We have two very qualified committee members. First member, Ignatius Niemikas. Also correct. Professor Niemikas has a long scientific career. After completing his studies in 1970 at the University of Delft, Belgium, he studied further at Purdue University of Lafayette, Indiana, USA, in which he received first his master's degree in 1972 and a PhD degree in 1978. So just to put it in perspective, our university was founded in 1974. So he was completing his PhD during that. After graduation, he worked at telephone manufacturing 2001 to 2002. From 2001 to 2002 he was professor at the University of Twente in the Netherlands. And from 2002 he was a full professor at Delft University of Technology, where he has been chair of the wireless mobile communication group and the telecommunications department. Currently, he has made a change to Eindhoven in Germany. And the numbers, the most recent numbers I have, just to put a bit of scientific career in perspective, is that he has published in excess of 300 publications, books, journals, conferences, and supervised more than 35 PhD students. I count. So these numbers have perhaps a few years old, more than later than incremental levels. Our the second committee member is Ahmed Shawky. He's from the State University. He's Fortaleza in Brazil. And also Professor Ahmed Shawky has received his Master's in Science, Master of Science and PhD degrees in Computer Science from the Trinity College in Dublin in 1978 and 1944. That's a few years after the university was formed. Only a few years. So he too has a long and impressive career, including positions at the University in Dublin in Ireland, where he lectured for more than 20 years. Sarajevo School of Science and Technology visited. He was at Kingston University in UK, University of Kebangsaan, Malaysia, Kebangsaan. Close. And he too recently changed position and is now full professor at the State University here, Fortaleza in Brazil. He also has a substantial publication list, more than 230 scientific publications in terms of books, journals, conference contributions. I do not have a number of PhD students, but I conjecture it's also substantial. Finally, I will briefly mention the local chairman, Mr. sitting there. Department of Electronic Systems, section of automation. I don't think you need further information for the group. The supervisors are from wireless communication, also this department, and also from wireless communication network. Last but not least, Professor also from wireless communication networks. I'm almost forgetting our main star, Ahmed Shawky. Ahmed Shawky graduated with Bachelor of Computing in 2006 from the October 6 University. That's in Cairo, Egypt.
It is. Yes, it is.
After a short break, he continued his education here at Aalborg University in 2009, where he achieved a Master of Science in Networks and Digital Systems. Since then, his work as a researcher and a PhD fellow at the Department of Electronic Systems until 2012. And from 2013 to 2016, he was TDC as a network planning engineer. He is currently Senior Capacity Planning Manager at Akamai Technologies.
Yes. Just started 1 month ago.
Very recent.
Yes.
The areas of interest are in capacity planning and management, wireless technology. So we have very qualified committee. We have a very qualified PhD candidate. So I leave the floor to you.
Yes. Let me allow you to welcome you to this PhD event. And as you can see, the title is Quality of Context Enhancements and Cost-Effective Radio by Cloud. Before I go into the technical aspects of the thesis, I would like to give a brief introduction about what is happening on the internet today. Today, thanks to the Internet of Things, we can see that a lot of different devices and platforms are gaining access to the internet. If you have an iPhone, if you have a smartphone, if you're having a gaming console or a smart TV, you're gaining access online. And due to this variety of platforms and devices being connected online, there has been a demand for new services in the form of applications that run on those devices and higher bandwidths from the internet service provider, whether that is like mobile provider or the wired service provider. So if we take a look at the new services, we can see that for the different platforms and devices that are running on the network today, there are various new applications. Netflix, Amazon Video is a source of video on demand, and they're not only running on your desktop anymore, but they're running on your mobile, they're running on your gaming console, and there's always room for improvement there. Other applications such as IPTV is also running to the network, and it's not only the application but also the technology that's coming. For example, 4K Ultra HD is coming out, and it will demand more from the bandwidth for these applications. Another form of applications that are emerging today is application migration, for example. So, to take a short example, that if you take a video running on your mobile and you're watching it and you come back home, you can then choose to migrate this video to your TV where you have a better resolution, for example. And this is a form of context information because the application and like the context-aware application knows information about your current session and the available devices that are on the network. Another very famous application right now is Pokemon Go, and it's also a form of context information exchange. Pokemon Go actually uses the user's location to exchange context information about locations of Pokemon in your world. So in this way, you're being more mobile while sharing context information about where you are, and you're also receiving context information about where those Pokemons are in the world. And thus, it puts a very demanding market for new services and applications, especially in the context-sensitive manner. If we take a look at the demands for higher bandwidth, this can be reflected in Cisco's forecast between 2015 and 2020. If we take a look at the graph, it's easy to see that from 2015 to 2020, web traffic is forecasted to triple, going from 50 exabytes per month to around almost 150 exabytes per month. But what's more interesting than this is that we get an 11% increase in video on demand and on IPTV. I personally disagree because with Cisco's forecast, because I think technologies like 4K will add more to the demand. It will reach probably around 25%. What's even more interesting is that Cisco forecasts an increase in mobile usage about 53% in those 5 years. This means that the trend shows that more users are going mobile. There are more mobile phones being added to the network, but not only this. It's also the amount of traffic, the applications that are running are generated. They're also forecasted to increase. With that in mind, I can start going through the outline of the thesis. From the title, we can see that the thesis is divided into two main halves. The first one is optimization of context quality, and the second one is cost-effective network planning. And there are two problems each part faces. First, how do I optimize the context application for future use? And the second one is, how am I going to meet this request for higher demands and bit rates to be able to reduce the cost for the internet service provider so he can provide those required bit rates forecasted by Cisco? Both outcomes of the contribution of the problems is a set of models and algorithms that are aimed to be targeted at the mobile service provider so that he could, so they are able to enhance the user experience. I will first start by going through the quality of context. To understand quality of context or context management frameworks, we need to understand the concept of context awareness. For an application to be considered context aware, it needs to have dynamic context, dynamic access to context information that is provided within a context management system. So, what does this mean? It means that if I assume a mobile phone, I have different types of apps running on it. Here we have a weather app, remote access app, even different network environments affect the phone. Also, device migration, as we mentioned, are one of the options. But for simplicity, I'll take the weather app and talk about it. In my phone, I have a weather app. This weather app would request information based on my current location about the current weather. And what happens is that it will request this context information from a context agent out in the network that is gathering the information about temperature. It then shares this temperature with a context management node, which in this case might be the server where the application is running at, or even be running directly on the phone. And then share it with the application and providing this context information. So in that sense, my device became context aware, or my application became context sensitive, because it has this dynamic context access to this information. So, how can I understand context management framework? To understand context management framework, we need to understand how context agents, context management nodes, and context sensitive apps will work together. Like we can see it in the figure, like on the right side, we can see different context agents running on the network, and they are collecting information. This information is about location, it's about noise, about temperature, as we mentioned in the weather app. It would then forward this information to the context manager. In this case, the context manager is embedded in the device itself. Sometimes this cannot be the case. The context manager could be a separate entity running on the network. And then it would forward that information to the context-sensitive application. Say, here you go. So, another term we need to understand is the context access strategy, or my methodology of obtaining context information between a context management node, as we can see from the figure, and a context agent. In this case, I am considering a reactive strategy, and please put in mind that there are different types of access strategy. There could be reactive, proactive, or periodic, and I will speak about that more later. Considering the reactive part, the context management would send a request message, D1, to the context agent, requesting information about context information. And then the context agent would respond with the message D2, right here, to the context management node. Now, as we can see, D1 and D2 contain context information, and therefore they have context size. They generate bits on the network. So the larger the messages are, the more load I'm putting on the network. So it will affect my reliability at some point if it's too large. We can also see a term called access delay here. And access delay is the time from sending a request message D1 to receiving a response message D2 at the context management node. This is the access time. How much delay does the message does it take to send this message? The longer this delay is, the more degraded the service would be. Again, if I revert back to the weather app, if you click on the app and it doesn't fetch your information very quickly, you will be frustrated. So this is what access delay is. Another term is context mismatch, and this happens when I send a request R1. At this point, event 1 has occurred at the context agent. So this could be temperature, for example, like 22 degrees Celsius. By the time I receive that information at the context management node, event 2 and event 3 has already occurred in time. This means that I'm receiving outdated information about the weather. It would be now, for example, 25, 26. So there is a mismatch between context information here, and that also affects reliability. why research quality of context? And the key word is reliability. Reliability of context applications is very important. If you would, for example, download this app and it keeps mismatching, as we saw, and giving you wrong information about the weather, there will be a cause of frustration and it will not be a very successful application. You would probably not use it again. In that sense, a context-aware application should respond to current events and not previous ones. And it's a very important aspect for reliability. So what is the problem with the quality of context today? We have identified in the thesis a set of parameters that affect the context reliability. In that sense, they are the information dynamics, or how frequently does the events change. And this is very important because if you're having a system that keeps frequently changing, then it's very difficult to get an exact match because it changes so frequently. So information dynamics affects the reliability. Type of access strategy, as we mentioned, if I'm using a reactive, if I'm using a different proactive, for example. A proactive event-driven, for example, would not use a request message from the context management node, but every time a new event would occur, it would send an update to the context management node from the context agent. That's a different access strategy. Another method to do it would be by time. Let's say I have a period of 5 seconds and I would like to receive an update every 5 seconds. That's another access strategy. Switching those access strategies will have a different impact on your reliability. So, the last one is the network properties. And this is the quality of the network line. How degraded is the network line in delay and packet loss. And it's also quite important because it affects it affects the reliability of the context information. The more the network performs badly or degradedly, the less reliable the information will be. There's another thing to mention is that those parameters are also dependable. And it becomes quite challenging to change one and see the effect of the other one. So the problem we're trying to address now is basically how to increase the context reliability while keeping in mind those context reliability parameters and their dependencies. So, what has been done so far in regards of quality of context? There have been several European projects such as Magnet Beyond, SPICE and eSense that have investigated improvement of context management frameworks. But it's just been recently coming into play that information about reliability is an important factor. And this has been shown in projects such as Sensi. Also, recent research such as quality of context, what it is and why do we need it, has acknowledged the fact that information about context reliability as a metadata might be of interest to see how reliable the information is. So, if we take a look at the similar work and how, the novelty of the work done in the thesis, we can see that research as a context quality model to support transparent reasoning with uncertain context have considered the age of information as a measure of reliability or context quality. And this is true, but we think that the age of information alone is not enough since it disregards the rate of change of context events. It does not take into, and to give an example for this, if you have two systems, one with a rate of change of 1 second and one with a rate of change of 1 year. The age of information, if you're sampling every 5 seconds, isn't really a measure of quality, especially for the one that's changing every 1 year. So it's quite difficult to see this. So the proposed approach that we take into account takes into account this factor. It takes into account also the parameter dependencies that we talked about. And also the thesis would consider the context mismatch as a good measure of reliability for context information. So what are the main contributions of quality of context? There has been two major chapters. The first is service degradation and context management frameworks. And what this chapter does is that it attempts to understand the network configuration, changing network configuration would affect the dependable parameters in context reliability. It presents a live test bed that is showing how context management framework work, and it would also present different results for network overhead and for mismatch probabilities. Later on that, we will move on to the next chapter, which is network aware dynamic context subscription management. And what has been done here is that we attempted, after understanding the network behavior and context management framework work and how the mismatch probability work, we would then take a look on how to use that information to extend the current context management framework to deal with optimization of context quality. The chapter attempts to understand how to assign context subscriptions to the appropriate strategy. So which strategy should I use? Reactive, proactive event-driven, proactive update, periodic update, or which class of service should I also assign those subscriptions to? So not only the strategy, but also the class of service. And finally, it builds on maximizing the reliability by aiming to lower the mismatch probability. I'll present now the test bed and the results that follow. We need to know two things here. That the test bed's aim was to see and study the behavior of context messages and access delays in a live scenario. We were also able to, this test bed was also done during the work in the Open project, which deals with application migration, and we had on-hand software for context agents and context management nodes that were running. Yeah. So it was also nice to see a realistic scenario for a context management framework. We can see the test bed in this image. On the left side of the network, there is a context agent that connects to a switch, that then connects to a router. On the right side of the network, we can see a context management node that also connects to a switch, that also connects to a router. Both routers then are connected with a 10 megabit per second bottleneck that emulates a wireless link. And there is cross-traffic being generated on both sides of the network. Now, how do we evaluate the results? We need to understand that during this test bed, we did two different sets of scenarios. One for expedited, for best effort traffic, which is a classless type of traffic with no traffic prioritization. The other one for an expedited forwarding traffic class, which is a prioritized traffic class in the diff-served domain. If we take a look also, we find that we have considered different context sizes, varying from 10 bytes to 10 kilobytes. The context size is the size of the message or the context information that's being sent from the context agent to the context management node. Finally, we were able to get, using delay information, we were able to calculate the access delay CDF, or cumulative distribution function, and we were able to use those measurements into plotting MMPR results, or mismatch probability results. This table shows the results from the network traffic, and as we can see, they are done from 10 bytes to 10 kilobytes. The best effort overhead and expedited forwarding overhead shows that for small context sizes, there is large overhead. So, like the smaller data sizes are really large. If I want to send 10 bytes, I will have to get in return 2,993 bytes in overhead, which it's not proportional if I'm sending 10 kilobytes, for example, where the increase is just 3,990. And the same behavior also can be seen for both types of traffic classes. So this is an interesting information to know. The mismatch probability results, by using the information about access delay, we were able to plot the CDS, we were able to plot the MMPR results. And if you can see the x-axis here, it shows the mean event rates, while the y-axis would show the MMPR results. And they're done for the two separate classes, like for EF and for best effort. And this is where we can see this bullet that says prioritizing traffic clearly benefits reliability. So it means that the prioritized traffic class has a much lower MMPR than the non-prioritized one, as we can see here. We can also see that there is a difference in when we are using different context sizes, like this is 2 kilobytes and this is 10 kilobytes. There is a difference also in reliability or mismatch probability. So the lower they are, the better the information, or the more reliable the information will be. And in general, we can see that mismatch probability is a good measure of context reliability. So, the testbed results summary. We have seen what the behavior of context size and context mismatch probability can be in a live scenario. We were able to show how traffic prioritization may affect the context quality. We've seen different results for overhead and mismatch probability and how the different classes behave differently. Results also showed that smaller context sizes had much larger overhead. And this is definitely something to be investigated. And finally, we showed mismatch probability results for the different classes and how that prioritizing traffic may benefit the context quality. And after examining all this, we have decided to go on further by trying to optimize context reliability by minimizing the mismatch probability. And this is what the next part will show. So, as we can see here, this is an optimized context management framework subscription management. The main contributions or extensions over the regular context management framework, and we're building here over the open context management framework, just for the information. That we can see a subscription configuration algorithm that runs at the context management node here, and a network performance prediction module, right, that runs right here. What happens is that we are trying to optimize the context subscription process. And this happens by trying to understand how much degradation will, or not how much, or how utilized the network would be and how the network quality would be after adding an extra subscription that comes in. That's why the algorithm here will request information about delay and packet loss if I add an extra subscription to the network. And then the network performance prediction, as you can see, it holds information about the network performance, so it monitors the network, and it provides information on how potential additional traffic will change the network. It then would reply and say, okay, this new subscription, that much delay and packet loss. And then the algorithm would go on trying to figure out how do I optimize the context reliability. So, what is the problem that we're trying to solve? First, which strategy to assign to the new context subscription? What kind of access strategy am I going to assign the new subscription? The second one is, which class of service would I also put that subscription on? So that's also something to solve. The aim is to increase the reliability by reducing the mismatch probability, and this is known. And this is why we have introduced a new, or developed a new scheme that targets at minimizing the average MMPR, which is called the global mismatch probability. And from the formula here, we can see that it is the sum of all active subscriptions in my network divided by the total number of the subscriptions, of the active subscriptions. A quick model overview. So, if I have n-1 active subscriptions and I get a new subscription n, what would happen? First, I would calculate the strategy utilization increase for the we're considering three different access strategies here: reactive, event-driven, and periodic. What will happen is that I will, for each of those different access strategies, I will calculate what is the potential traffic or utilization increase, which then will be forwarded into a network model that will give me information about possible delay and packet loss. The delay and loss information is then forwarded into an MMPR calculation block, and then I will receive MMPR calculations at the global MMPR, and the subscription or the access strategy that will result in a minimum global MMPR is the one chosen for configuration. So how do we evaluate those algorithms? A series of simulations were carried out. 50 subscriptions were sent to the context management node. The simulations will compare the intelligent method or the new method that we proposed to assigning network strategy to default constant access strategy, where if all 50 subscriptions would be reactive, for instance, or if all 50 subscriptions would use an event-driven approach. We also assume that all 50 subscriptions share the same wireless network, so it's fair to compare. And we show results for two different scenarios. The first is a best effort scenario, and the second one is a scenario that assigns traffic to two different classes. So we have two different classes where we can assign the context to. I'll start going through the simulation results now. And as we can see here, both optimization scenarios have a maximum capacity of 10 megabits per second. However, for the class-based scenario, we have two different classes as mentioned. The first class with 9 megabits per second capacity and where the utilization will be. And the second one is 1 megabit per second capacity with 0% utilization. So, first, this is the results for the best effort scenario. We can see that the mean global MMPR for 20 simulations, each having 50 subscription requests, is being presented in this graph. The subscription distribution for the optimization algorithm is 31.45 event-driven, 18.55 reactive, and 0 periodic. And when I zoom in a little bit here, we can see that this is the optimization algorithm, and there are two lines because we have two versions. The first version runs, as we said, and it tries to select the subscription that will minimize the global MMPR. And the second algorithm attempts to optimize all active subscriptions that are currently active now. So it goes and iterates over the active subscriptions and tries furtherly to minimize the global MMPR. And we can see that the black one is actually version 2 that tries to furtherly reduce it, and it's a bit lower. We can see there is a little gain here. However, both optimization algorithms, both versions, perform better than if we would use a single strategy for all active subscriptions. And this can be seen here. It's substantially lower than event-only or reactive or periodic-only. So the algorithm was successful and the MMPR reliability are higher if we use this method. A class-based scenario. It was worth noting that this was under 90% utilization. That means that we utilized the network, the 10 Mbits, with 9 megabits per second of cross-traffic. For the class-based scenario, we looked into a more congested scenario. So what would happen if I would go 100% utilization? Okay, and that means that the class 1 would have 10 Mbits, and it can only serve 9. So it's overly congested, we can say that. The same holds, 20 simulations, 50 subscriptions, but now we have also a class distribution. And what we could see that class 1 almost had 0.2 subscriptions. So almost no subscription wants to be configured over in class 1 because it's overutilized, which is very interesting. But instead, the rest would actually prefer to be on class 2. From the subscription distribution also we can see that mostly is event-driven, a part is reactive, like 18.55 reaction, 0.2 were periodic, and there was a small number of rejections as well. And rejections would occur only, or they were programmed to occur only when the MMPR would reach 1. So it's 100% you're reaching an MMPR, so we chose to reject that subscription. If we can take a deeper look here, then we can see that this is the classless. So this is the old algorithm, or not the old, the algorithm I just showed before. And this is the new class-based that splits the traffic. Under high utilization, when I'm 100% utilizing the network, then this one would perform much better than this one in the global MMPR aspect. So there is also gain to split the classes under high utilization. So, I will go through the conclusions for this part of the thesis now. We started with a problem, and this problem was how to increase context reliability while keeping in mind the context reliability parameters and their dependencies. In attempt to do this, we have investigated the test bed that I presented, and we saw results for network overhead and how they were large, or like network overhead for smaller state sizes was quite large. And this definitely needs further investigation, because it might be beneficial for me to spend some time to reduce the context size with compression techniques in order to gain reliability. On the other hand, I'm also using time, which will affect the access delay, so it's not an easy matter to solve. So this could be very interesting to see. The results, the thesis also presented the extension for the open context management framework that we discussed, and how we added an extra network prediction module that was able to, along with the subscription algorithm, that was able to assign better, or not better, but smartly assign context subscriptions. Finally, we could see that the algorithm successfully maximized context reliability by reducing the global MMPR, or the MMPR of all active subscriptions in a network. Yes, I will now move to the network planning part of the thesis. The main contribution here is a chapter titled An Automated Planning Model System for Radio over Fiber Heterogeneous Wireless Networks. The contributions or the outcomes of it are a novel methodology for implementing an automated planning tool for radio over fiber architecture. The chapter also reviewed a case study of how do we compare the ROF technology planning in the other hand to the regular wireless planning that we have today. So this is also provided. So why do we need a new planning method for radio or fiber, or a planning method in general? We can see from the intro that I gave, there is an increasing demand for higher bit rates. So users would like to have more bandwidth on the network. At the same time, there is an increasing complexity in wireless systems, which makes the planning process more complex. This leads also to demands from 4G on meeting the higher bit rates, and this is accommodated for by reducing what we call the cellular cell size. And this is not in the ISP's interest, because the smaller the cell size is, the more deployments of base stations that will be. And base stations here costs a lot of money. Some of them can reach up to, like, if you're having the full one, it will reach around $150,000 US. But we'll see a price comparison later. So due to all of this, we are in need of a new architecture and a new planning tool that is able to carry it out. First, we need to understand what radio over fiber brings to the table. Radio over fiber aims to replace those extremely expensive base stations with inexpensive radio antennas. The radio antennas, as you can see, would then connect to a central unit right here. So those are the remote antenna units, as we call them, or the inexpensive antennas. They would connect to a central unit where all the complex signal processing will take place in a joint processing. So I can even serve more than one with a single joint process. And this could be quite beneficial, because I am taking all the complexity out of the base station and I'm making it, I'm distributing it over a single entity that is able to serve multiple of them. So, what is new and what is the novelty? Today, or what's happening today, is that in the network planning aspect, we don't separate radio planning from fiber planning. And I can say this because I've actually worked as a network planner for 3 years. It's totally different worlds where we just need to say, okay, we need to connect these amount. So the novelty here is that the automated tool just uses GIS data, which is Geographic Information System data, and as an input, and then it will provide automatically results for the radio planning and for the fiber planning and also the equipment placement, just using an input of geographic information. The tool would then, after receiving this GIS data, it would combine heuristic approaches and pathfinding algorithms in order to place all of these, or to produce all of these results, the radio planning, the fiber planning, and equipment placement. And finally, due to because prices are very private, like vendors don't speak much about it, it's very difficult to compare pricing. And therefore, it is quite interesting to see how much would a new architecture actually cost or save if we were to implement it. So, for the thesis, we took this geographic scenario, the Danish municipality of Aalborg. The GIS data was provided by TDC, and therefore, this is why we chose it, because we only had available information about TDC at university. And this information, we were able to plot the road network for Aalborg and the population density, or how much the user are distributed in Aalborg. And it's quite important to know this, so you know how much of the population you're actually serving. Okay, so how does the automatic planning tool work? In the radio planning, after inputting the GIS data, we were able to solve, okay, we have a problem now. The problem is how many REUs or how many antennas do I need in order to cover a certain percentage of the population. In that case, I assume 97% because no service provider would cover 100%. It's too expensive for them to do that. So we're using like heuristic approaches such as 3D algorithm and genetic algorithms to find how many REUs will be active to cover those 97%, and then I get an output of these sets with users predefined limit on. For the fiber planning, after I find the REUs and the locations of the central units, I need to assign those REUs to the closest central unit. So I use a pathfinding algorithm, and in this case we use the A-star algorithm to assign CUs or central units to the REUs, the remote antenna units. We also, after assigning them, we needed to connect them with fiber, so we used the minimum spanning tree to connect the control units to the REUs. We can see here a sample of the results generated by the planning tool. On the far left, we can see the 3G radio planning, and this shows the 97% coverage of the entire users in Aalborg within cells. You can see that those large cells are for rural area coverage. The green ones, the not very small ones, are for suburban, and the red ones are for urban, like downtown. And you can see they get smaller the more concentration of potential users are. Most people live in downtown, that's why we have smaller cell sizes to cover them there, so we have more capacity. Equipment placement, we can see that the squares show the central units, and the triangles show the REUs. And if we take a set that has the same color, it means that a central unit serves those REUs with the same color. And finally, we have some fiber planning results here for the central units. We chose a simple ring connection because despite of all the fancy structural quality of services topologies that are out there, internet service provider till date use a ring topology due to its cheapness. It's very cheap and very effective method of providing protection. So it's still used till today, quite frequently. I'll move now to the deployment cost comparison. The focus was here on visibility and deployment cost. And in order to do this, we assumed that there is no equipment for the current wireless technology. So we could compare the new one to the old one. So both are built from scratch. If we take a look here, we can find that for a regular implementation, you would probably need 69 base stations. But for the proposed one, we can see that the REUs would then you need 58. And in a worst case scenario, if you could not do joint processing for all 58, you would need 69 different joint processors or central units on their own. And those, we calculated this based on this worst case scenario. So, what are the equipment costs? From what we could gather online and what was available by sometimes mouth to mouse, we could find that the regular base station would normally cost, and this is a medium power one, so it's not the most expensive type, would cost about $15,000 US. However, a remote antenna unit would cost about $2,000 US. And the central unit would cost about $4,000 US. So when we combine that with the numbers we had, we can see that in a regular implementation, the base station would cost a little bit over $1 million, while if I combine the remote price with the remote antenna unit price with the controlled unit price, I'm getting somewhere about $400,000. So in this particular scenario, Aalborg, we're saving 60% of the money, and if you go to an ISP with this amount of savings, you'll be a hero for life, I guess. So, what can we conclude from this? We showed a method for planning an implementation of radio over fiber technology. The method was as automated as possible and built over GIS data as input. You can see we successfully built off a network from scratch using this geographic information system. And finally, we showed a price comparison that shows the radio over fiber remote antenna units and central unit considerably cheaper than the regular base stations being deployed today, being in mind that we actually used the medium one, not the too expensive one, because they do cost up to $150,000 US at some point. And finally, we could see in the particular scenario of Aalborg that we were able to save about 60% of the capex or the capital expenditure in this. Yes, that was all. Thank you very much for your attention.
Thank you, Ahmed, for a nice presentation. Thank you. We're going to take a short break before we begin questioning. I think it will take 15 minutes or so. Fortunately, there's no clock in here, so I cannot point at the clock, but I will shout out when it's time. So we'll take a short break. Please remember, if you do have any questions, tell me in the break. No need to tell a question. I will not be able to answer it anyway. But just notify me if you have 8 or more questions.
I will be here also. Yeah, I will come. I just don't want to be here when